really appreciate you all coming out to see the latest and greatest products and technologies to make life great for developers. And our ambition here is no less than that as well. I'm James Coles, and with me is the brilliant and charming Lou Amadio, and modest too. And we will be running through the latest Windows IoT innovations, what we're working on, and how we're with you as developers all the way through your journey building IoT devices. Now, I have 4 live demos set up here, so we're going to see how that goes. And so if fortune smiles upon us, you'll see 4 live demos going, and we'll see where you get from there. Great. So let's get started. So why do people build IoT devices using Windows? You know, we actually recently went and asked a great number of them that question. We asked them, what are you doing with it? Why are you choosing Windows? What's in it for you? We know you have a lot of alternatives when you build an IoT device. Why do you choose Windows? And of course, on the screen here, we have some of the kind of the synthesized answers that we get. But you know, let me just walk through that a little bit. We hear it enables us to get to market really quickly. That's probably the number one thing that we hear. You know, we hear that the amount of time we have to put into development and marketing, that affects our competitiveness in the channel, right? And so Windows IoT helps us reduce the cycle that it takes for us to get a product, revise a product, and keep a product up to date. And if you think about the alternatives, or if you're going to use another operating system, generally you're going to have to staff an operating system engineering team. It's just a fact of life with the other operating system choices. With Windows, we do that for you. That means the product is at commercial scale right from the get-go. So again, this is what we hear back from our customers who use it. They also appreciate build. Right? They appreciate the code samples and the templates and the technical training. And, you know, if you were on the floor, you saw MS Learning. There's a ton of that. They appreciate all that as well. They appreciate that it is up to date, right? It is a supported operating system across all of our platforms. It's 10 years of support. And for a device maker, that's really important. And the fact that Windows provides that on a wide variety of silicon spectrum is important. And then, of course, they appreciate that it's ready to go with the cloud. You know, what I have is smart on the slide here. And, you know, Microsoft is the company with a major top-tier cloud offering and a major top-tier operating system offering. And so that enables us to have them work together in smart ways that, again, reduce the time to market so our customers can spend their time on their application and their solution. And that's really important to them. Now, this is the portfolio of Windows IoT editions. It goes from the small side of Windows 10 IoT Core, which is used for very small devices. And we have a number on the expo floor if you've seen them. Please feel free to stop by and check them out. A very low BOM cost. It's good stuff. Our bread and butter is Windows 10 IoT Enterprise. Now, that's the full edition of Windows, and everybody appreciates they can run their entire ecosystem of applications and code that they've developed over the years on that platform. And that's really, you know, that's kind of our big seller. I was just recently having a bunch of dental work done, and my dentist had a Windows 10 IoT Enterprise scanner that she was scanning inside my mouth, and she was annotating, and she was literally inking on it right there. Thank God she was using IoT Enterprise. I would hate for that to get hacked while my mouth is getting work done, so I felt safe and secure about that. And then, of course, we have our IoT server product, and this is if you have kind of a dedicated data center installation, perhaps out on a oil platform or a ship in the North Sea. This gives you the great capabilities of server in an isolated platform area. And all of these 10 years of support across the entire thing. We've got it all. I'm going to dive into a little more detail now. These are a number of the things that we've achieved recently, I think since I saw you last out here last year. And of course, we have our long-term support release came out, and a number of other features available on that platform. what's coming next, or actually really even now for some of these, are what we have up here. So we have a lot of Azure focused, again, work done here, as well as Shell Launcher and our Qualcomm work there to broaden the experience of those devices. Now, these are the ones I'm going to talk about. We're going to talk about all of these plus a bonus demo of our Windows CE work through the rest of this talk. So again, we're going to have 4 live demos. And without further ado, I should dive into those. So first I'm going to talk about Azure IoT Edge. I believe most of you at this point are going to be familiar with the Azure IoT Edge application pattern. You know, this is an Internet of Things, which requires an Internet and things. The things send up signal. There's reasoning done. Actions are done. Well, now we can move that compute actually down to where the data is. We move the compute from the Internet to the things. You know, that's Azure IoT Edge in a really quick nutshell. We're thrilled to announce that Azure IoT Edge is generally available now on Windows. And so it's ready now. This is on Enterprise. Server and IoT Core will be coming very shortly. And again, it's our bread and butter SKU, so we led with that one. For folks who have been using the preview, you'll notice some significant strides forward in the capabilities of Azure IoT Edge on Windows, largely around the capability of the containers. So there's access to all of the buses that we would expect an IoT device to be able to access, as well as access to the GPU for hardware-accelerated machine learning inferencing, some of which we will show you today as well, and we have that down on the expo floor. Again, you know, Sam said in his talk that really a camera on an edge device is the ultimate sensor. It's the nearest thing to humans, the ability to see and sense about the world. And so the big value scenario in edge computing is machine language inferencing. And so for Windows, Azure IoT Edge on Windows does totally support on-device AI inferencing. Currently what you would do is you'd build a model in Azure ML, and then you would export that via Onyx, and I'll show you that in a bit. There's some other ways as well. You'll combine that with some .NET code that as Windows developers you're all familiar with writing. You'll create a container from that, and then that will allow you to take advantage of Windows ML. So another great value of Windows is Windows ML is the only evaluation engine for machine learning with 10 years of support. Like, who is doing that? Microsoft's doing that. And so CPU evaluation is very fast, and also it allows you to be not locked into any one GPU vendor, and that's very important to some of our industrial customers who don't want a single source for any of their products, and Windows ML enables that. So on the show floor, we've been doing a hands-on lab that's been well received, and I'm going to show it to you now, hopefully if my machine wakes up from sleep properly. And I just wanted to run through the architecture from what that is real quick. So the idea is we start in the custom vision service, where we will train a model using some images. We will export that to an Onyx 1.2 format. If any of you were around in the previous talk about the value of Onyx, this builds on that as well. That's going to be deployed to an Azure Container Registry as a container. Azure IoT Hub will be used to deploy that container to a device. In the case that we've been doing today, a Windows 10 IoT Core device, and that's what I'll be showing up here in a bit as well. That sends the inferenced telemetry up to the IoT Hub, which will then send that to Azure Time Series Insights, where our eyes can finally receive it. And so we can see what's happening there. So one other thing. You can try it yourself. There's a link here, and also there'll be a links page a little later on with this link repeated as well. So this is what we're showing on the floor, and you can certainly give it a roll. I encourage you to do that. Again, with .NET development skills, you'll see how Windows ML and .NET come together for that. Okay, so now I'm going to show you my demo, and I'm going to switch over here, and Greg is going to show us my little setup here, and I will narrate it just a bit here. So as you can tell, let's come up here. This is something that I put together myself after a trip to Home Depot to get the point across. Oh, I did this actually for a lab for my 11-year-old daughter. So I think we have a child or two in the audience, and we use some of her toys in this lab. So I decided to bring those in as well because they're really visceral and you can really see them. So I have it right now focused on this little squishy lamb, and we're going to put my piggy bank in here next. Anyway, so I've got 3 machines here with 3 different cameras. I have a Windows 10 IoT Core running on an AMD V1000, which has a really strong GPU in it. I've got a Intel Minnow board, which is very low cost and at a sacrificing capability, but that's a choice you can make. And I'm running Windows 10 IoT Enterprise on an Intel Core i7. This particular one doesn't have an additional video card. It's using onboard video. The same application that I'm going to show you is running on all these in a container that's been deployed via Azure IoT Edge. Now I have 3 different cameras. These are off-the-shelf cameras. The great thing about Windows is it has a full media stack, so any camera that Windows can see will work for this. And they're all taking a look at the item that I have up there for inferencing just at the moment. So I'm going to walk through this. If we could get just a little higher, maybe we could see from the top-ish view here. Might be a good view so that we can see we've got 3 machines, the 3 cameras, and then my item on stage. OK. Thank you very much for that, Greg. So let me jump over here. Great. So let us start, not in the Badlands, but on Custom Vision. This is Azure Custom Vision, which is a great service. Anyone who's doing anything with machine learning and computer vision, I highly recommend checking out Custom Vision. It's really economical as compared to making your own model. It's really simple and easy to use that really anybody can do this. So what I've done here is I've taken a handful of images of each of my items, and then I've trained them. So let's see if I can train here. You'll see how fast training is. So fast, it's not going to happen. All right. Trains very quickly. So once I've trained my model, drum roll please, from this interface, I can go ahead and export it. Now that's what I would show you, is me exporting this as an Onyx file. Our network doesn't seem to be totally cooperating here, so I won't be showing you that. But trust me, so this is where we would export it. So I would save that Onyx file that I exported from my Azure Custom Vision service, and then I'm going to bring it into my code environment. So this is a fairly straightforward .NET application. You'll see this Custom Vision file is up here, which is the one that I would have exported to. So let's take a look at program for a second here. Let me get more full screened. All right, so this is a .NET application that is going to pull in Windows Platform APIs. So we can pull in these various Windows Platform APIs. Of course, I'm pulling in the Windows.ai.machine learning, which is the real value here. But as well, I'm going to pull in the graphics. I'm going to pull in media. And those are so that I can form my image into the right size and shape for the pipeline that's going to go into machine learning. And of course, I want to use storage to pull files off disk and in a way that Windows AI would like them. So let me just kind of run through what I'm doing. So I'm going to get the options off the command line, which is where I've specified various things here, which is not that interesting. Then I'm going to initialize the Edge runtime, which is real simple. Now I'm going to get into Windows ML here. So Windows ML generates this scoring model class for me, and so it provides this create from stream async method on that. And so all I have to do is I've loaded up my model file, and I've provided that to the Windows ML scoring model file it generated. Then I'm going to open my camera as a frame source. And those of you who are familiar with the Windows Media APIs will find a lot of this code very reassuring and common. Basically what I did is I took this link here. I took the docs.microsoft.com frame source code, and I just put it into a file. I just made a class in it. So I took the absolute code right off of our documentation, and I've used that to open the frame. So I'm going to get the frame. get the video frame out of it. And then I'm going to, again, call model.evaluateAsync, which is a Windows ML generated class that allows me to go ahead and not have these things up here. Sorry about that. Oh. Drama in demo land. Okay, this Windows ML function here, method, allows me to just get scoring right out of that. I'm going to convert that to JSON because JSON is what Windows IoT or Azure IoT Edge wants to see. Then I'm going to use the module client and I'm going to send that event right up to the cloud. And then I'm just going to loop forever. It's very simple. Simple.NET code and using the power of Windows ML. So then on the other side, I can look at time series insights. My model's still loading in custom vision. All right, so let us look at this. So this is Time Series Insights, which is another fantastic tool from Microsoft that really allows you to visualize the data that you have coming in. So the first thing I'm going to look at here is my devices I have connected. So I can see I have 2 devices connected with a very long name. My Minnow board and my PC decided to connect. My AMD machine didn't quite do that, but that's why we have 3 things, so that if they don't all work, your demo still works. I can see that I'm getting in about 850, 870 from the Minnow board, and actually what I'm seeing, so I'm getting in about 9 events per every 5 seconds. That's my interval from the PC, and I'm getting in a smaller number of events because of the performance on the Minnow board. So now I can come and see what I'm getting. I like the heat map as a way to visualize this. So these are the various possible outcomes in this model so far. And the way the Time Series Insights UI works here with this heat map is it's going across time. So we can see that until 14.10, when I switched it, I had the blue lamb up there, and you'll remember it was there. And then I switched over to the zebra pig. And so starting at this time, I can see that I was getting in a number of results at that time. So I can see what's coming in. Now, you're professional developers. You're paid to write code, make solutions, so you're probably not going to use little stuffed animals in your professional life. I get that. So let me translate this a little bit into how you might actually approach this. Imagine a steel rolling plant, like I showed last year, with cameras looking at the steel and evaluating the defect levels in that steel. And then this lets us see over time for any one of the machines or stations kind of what level of defect we're getting at that time. So let's say during this time period I had a low amount of defect. This time I had almost none. At this time, oh, maybe I got spiked with a couple little defects right there. And Time Series Insights will let me visualize that in a really straightforward and easy way. So that is the demo. Let us switch back to the other thing. No. Great. Cool. So everything I showed here is ready now. This can be put in production now. There's hardware you can buy now. The operating system's now. Edge is now. It's all there. I do want to walk into the future just a little bit because I also enjoy spending time in the future. And in the future, we'll have tighter integration with Azure Machine Learning. So this loop here is the Azure Machine Learning workflow that is used today. And today, it makes it really easy for data scientists to go in and train a model, Python, use the right libraries and everything, and then put that right out to Azure IoT Edge. Coming shortly, we'll be able to create Windows containers directly from the UI or the SDK in Azure ML as well. And then we are also, later this year, going to be releasing a specialized Windows container for machine learning. And the idea is that this focuses on the Windows ML stack. As I said, it's the only inferencing engine with 10 years of support It will be in a container. It will also include the top-notch media and audio stack that Windows provides. And that's valuable because with machine learning, you need some data to reason about. And often that's media data, audio data, video data, image data. That's a really common use case. And so having a Windows stack there to make that really use that data well and prepare it well is a big value. I'll also point out the size. So we are targeting a 350 MB on disk size for our Windows ML container. And before I did the talk, I pulled the TensorFlow images, did Docker images on that. And for just the CPU image inferencing container, that's 1 GB on disk. And the container offering GPU inferencing is going to be 3.5 GB on disk. So you can see we're a factor of a lot, is that factor of 10? That improvement on size. So we think that will be exciting as well. And again, that'll be coming later this year. So this is my reminder of links. Please go ahead and give Azure IoT Edge on Windows a shot. This link will take you to the Windows installation page. I encourage you to do that. The hands-on lab that we were doing earlier and that I gave a sneak peek on is also available here. Please open a GitHub issue if you have any questions or concerns, or hit me up through GitHub on that. And then we have a whole set of samples showing how to do really everything with Azure IoT Edge on Windows specifically. So SPI buses, I2C buses, serial, the whole thing is all shown on our samples page, so please do give that a shot. Okay, so I talked at length about Azure IoT Edge on Windows, and that's an important and valuable technology. It's not the only thing in Azure IoT, though, right? There is more to Azure IoT than Azure IoT Edge. So we've been working hard to improve Azure IoT generally on Windows as well. So I'm going to walk through a handful of those now. We're also announcing the general availability of the second version of our Azure IoT device agent. So that's available now. Again, there's a link here if you want to check that out. What this does is it allows the full suite of remote device management that you might get from, say, connecting with Intune. That is also available to folks who write applications through IoT Hub. So it quickly and simply makes Windows management available to Azure IoT Hub using the same management capabilities under the hood that Windows has provided for years or decades. And so those are all available to put into IoT solutions as well. So this makes it really easy to, at mass, control IoT devices using the management capabilities that Windows already has built in. We've also announced the IoT Plug and Play initiative, and so our Windows device agent will also support that when it's available. I believe this is the fastest way to create a device that's certified for IoT Plug and Play. Really, if you grab our code, you build it, put it on your device, you're ready. Now, that thing is ready to be managed at scale using IoT Plug and Play. And so we think that will be really exciting when that comes out. Okay, so I've talked a bunch about device management, but really you don't make an IoT device to manage it, right? You make an IoT device to sense the world, to send those sensings to the cloud, and to receive commands back to change things about the environment. And so I wanted to give you a little sneak peek on some work that we're doing. We're building a sensor bridge from Windows to Azure. And the idea here is, you've plugged things into Windows before, I'm sure, and seen that generally speaking, those things are recognized. You can put just about anything into a Windows machine and Windows will know about it. So we make it then really easy for Windows to be able to make that available to the cloud as well. So you do have to do a little bit of wiring to say, this is my thing, I want it to go to the cloud. We're going to show you that in just a second. But generally, it's super easy to do, no code required. There is a little scripting that will show you, but you don't have to write up code to be P&P compliant as long as you have a Windows device and a sensor that Windows recognizes, which is pretty much all of them, really. And the other beauty of it is there's no need to recertify your IoT plug-and-play certified device once this is running, because we know that with the Windows sensor bridge, you're already IoT plug-and-play compliant. So this is in private preview. Those of you who are interested in this, please feel free to hit up this email address that's on the screen right now, and we'd be happy to work with you on the details of the sensor bridge, yet to be named. So that is what's there. Okay, so I'm now going to ask Mahmoud Hussain to come on up. Mahmoud is a program manager, I think the primary program manager, on the Windows sensor bridge here. And Greg is also going to come up with his skillful camera work. And we're going to show you this in action. So,
thanks, James. Thank you. Thank you, guys. So like James said, right, we want to be able to easily connect any sensor that can already connect to a Windows device. So before we get into the demo itself, let me walk you through the setup that we have here, the fancy little setup. So over here, I have a commercially bought carbon dioxide, carbon monoxide sensor. This is something that you might typically find installed in an office or a factory, right? It's nothing special. This does a bunch of things other than carbon dioxide, like humidity, for example. Now, this is connected via an RJ45 cable, and I shouldn't step on that, to this device over here, which is in the IT closet. This is a breaker board. Right now, there's just one device connected, but you can imagine if you have multiple sensors, this is how they would terminate into the IT closet. And I have a jumper cable here that's connecting over to a Modbus adapter. This sensor is talking Modbus over RJ45, and that's what we have here. And this is then connected to COM port on this industrial PC. This industrial PC is running Windows IoT and all the connections that you would imagine. Now, this sensor over here isn't what you might typically consider to be a quote-unquote smart sensor. When I take it out of the box, it's not going to connect to Azure or AWS, any one of those cloud services. So how do we do that, right? The combination of the sensor with the sensor bridge is how you make a smart sensor. So let's see how you do that. 8. Thank you. And it, of course, is timed out. So the first thing that you need to do is you need to create an interface towards Azure that says, this is the sensor that I'm expecting. These are the properties that I'm interested in. And that's what you have over here. So this JSON file over here is telling me that, hey, I need an interface exposed here, which is you're seeing here. And then I'm interested in certain properties. I want the firmware version, the property of the model name, and so on. I want the carbon dioxide status. And I'm also defining a command that allows me to clear the alarm once it's set. So this is what I am exposing on the Azure side. Now, on the device side, I'm already talking OS APIs, but I need to let the device know how to talk to the sensor. And to do that, I have this user manual that I've brought up from the manufacturer. As you can see, this is the same user device over here. And the manufacturer here has provided a handy little table that gives me all of the Modbus mappings. So you can see over here on address 4001 is where I read the carbon monoxide reading. So on 4002, which is what I'm interested in, is carbon dioxide. So this is literally what a manufacturer would provide anybody. Now, what do I do with this, right? I know now what the sensor is putting out on the RJ45. I need to be able to bridge that to the device I have. So let's go back to the JSON. And there's yet another JSON over here, which tells the sensor bridge running on the PC, on the industrial PC, how to talk to this sensor. So first, what I do is I am defining a Modbus device. And I know that I'm connecting on the COM port. And here's the COM port parameters. This is the same interface ID that you saw in the previous file. And then right here, I'm using the address 4002 because I know that's where I read my carbon dioxide. I'm doing the same thing for a bunch of properties, the alarm status, etc. And here, for example, is the command to clear the carbon dioxide alarm, which is at this address. If I write a byte at that address, it gets cleared. So that's it. Those are the two files that a device builder will have to go and edit, and now they can get the sensor up to the cloud. So let's see how that happens. So let me bring up a application called the Device Explorer. This is available on GitHub. If you follow the announcement on the IoT plug and play, it's available on GitHub over there. I've already plugged in the IoT connection string. This is talking to the IoT hub already. So if I look at the devices tab, it's going to take a little while for it to come up, and hopefully it does. So here I'm looking at the device twin and a lot of the properties that I just defined. So I know that this device is working well. Let me check the telemetry. This again takes a little while. So that as soon as that comes up, we'll be able to see the telemetry from the device. And here we are. We're seeing all of the latest events showing up. Now let's try a couple of things. This is measuring carbon dioxide in this room. I'm going to lower the threshold all the way down and see if it triggers an alarm. So Greg, if you could focus on the carbon dioxide alarm right there so you can see that happening. So right now you're seeing the threshold is 100, and I'm going to change it to 100, and I'm switching because it happens really quickly. So I changed the threshold. The threshold was lower than what it was set to, so the alarm went off. You will see a red light if you can that's going off, and it's a persistent alarm. So I'll switch it back right now, back to the old threshold. And now let's go back to my screen, and let's look at a command to clear this. Right? So if you can see, I'm just using a checkbox. And before I submit, I'm going to switch back because, again, this happens too quickly. So I'll submit here. And hopefully you saw that it went, that it got cleared. And I verified that it is indeed cleared. Right? So you can see that the carbon dioxide reading, it's a little shaky, but it's in white. So that was a simple example. Thank you, Greg. So that was a simple example for how you could connect a sensor that we bought off the shelf to Azure, and all you had to do is edit a couple of files. I can do the same thing with a USB-connected camera. I can send the telemetry up to Azure. I can do local processing just like the ML model that James showed. Any sensor that connects over serial, I can connect to. Any sensor that connects over USB. The key point over here is that if a sensor is already exposed to Windows, if Windows can recognize the sensor, then we can have that sensor exposed to Azure via the sensor bridge. So that's it. Thank you, James.
Great, thank you very much, Mahmood. And the Windows Sensor Bridge is a great way to leverage Windows to be able to easily get these sensors up to the cloud and IoT plug-and-play aware. So that concludes our section on Azure IoT improvements. I'm now going to hand the floor off to Lou Amadio, who's going to walk us through a number of other client-side improvements. There you go, Lou.
Thanks a lot. Windows CE was released in 1996 when Windows Desktop could be installed from a stack of floppy disks. Now, if you don't remember what a floppy disk is, it's like a flat 8-track tape. It grew in popularity, and there were hundreds of devices, or actually thousands of board support packages, tens of thousands of manufacturers representing hundreds of millions of instances of Windows CE deployed in all verticals, from manufacturing, warehousing, even medical. So we're looking at how to migrate those systems to modern operating systems so you can take advantage of modern workloads, take advantage of modern security, and modern manageability. When migrating from legacy systems like Windows 7 embedded, Windows XP, or Windows 8 embedded, the translation from those operating systems to a Windows 10 IoT Enterprise is relatively straightforward. The APIs that you're likely using are still in the system. They haven't been removed, or most likely haven't been removed from the system. So you can take a binary that has targeted those previous versions of Windows, move it to Windows 10 IoT Enterprise, and have it just work. And we work actually really hard to make that, to maintain compatibility, because nobody wants to upgrade and find that things don't work. When we're talking about smaller devices, if you're creating a new one, you have a choice between IoT Enterprise and IoT Core. IoT Enterprise offers you the greatest compatibility, and it also works on higher-end CPUs, where IoT Core is designed for smaller class devices. However, there is a, how do we take existing Windows CE applications and run them on IoT Core? Since I joined the team, I've actually looked at how to do this a couple of times. How do we actually do API compatibility using detours or trampolines? How do we actually emulate GUIs and things like that? But we actually never, we always stopped working on those. because it didn't actually meet our goals. So what is the goal? We wanted you to be able to take advantage of the modern versions of Windows while allowing binary compatibility for Windows CE applications. All of those hundreds of thousands of instances of Windows CE represents a lot of software that's been built, a lot of expertise that's been built up, a lot of system integrators built businesses around this, and there's just a lot of software. So how do we actually take that software and migrate it forward? Now, the opportunity here is if you take those applications and you bring them forward, you can use modern techniques like machine learning, you can use modern long-term supported OS, and you can use modern manageability and connectivity. So about a year ago, I was lamenting that we weren't able to solve this problem, and I said, you know, I really wish we could just run Windows CE on top of IoT Core. My manager goes, why not? Why can't we do that? So he spun up a team that went and did this, and they came up with a brilliant, elegant solution, and I'm really honored that they are allowing me to talk about their solution today. So how does this work? Well, as you can see, we've taken CE and actually refactored portions of it, and we're running a significant amount of it inside of a Pico process. Now, a Pico process is the same technology that runs the Windows subsystem for Linux. When you start up the process, it has nothing in it. You just get a flat memory space, and then you can drop any kind of binary you want inside of it. We've taken Windows CE and split it into pieces so that most of Windows CE actually runs inside of this Pico process, and the CE application binaries run directly in this process, as well as any DLLs or other other components. Portions that actually can be directly translated to the Windows NT kernel, such as handling interrupts and timers and things like that, are handled in a system process, in a driver that runs on the Windows side. For higher level concepts like printers or network support, we actually have a process that runs outside of it called DKmon. You wouldn't believe me if I told you what that stood for, so we'll leave that as a mystery. So the way it works is when you have a API in your binary, executable or DLL, that calls through into the OS, if it can be serviced by the NT kernel, it'll go all the way through. If it doesn't, it uses a cross-process call to DKmon to service it and then return it up through the system process. So let me show you how this works. If we can have Greg come on up. We've been co-engineering this with Rockwell Automation, and I think Clint is actually in the audience. Thank you very much for the trials and tribulations of getting this up and running. We really do appreciate it. On the left-hand side, we actually have a Windows CE display that was built by Rockwell Automation, and they've shipped many, many instances of this. The application that's running on it is called the Super Juicer, and it's designed for applications where they're taking vats of material and mixing it. You got to keep that stuff stirring and mixing and deployed out to the product line. So as you can see that what we have here is a number of custom controls that visualize, in this case, a simulated level of material in each of the vats. Plus, there are motors that control the valves that actually will distribute the material around the factory. If a worker were to click through any of these vats, you can actually get details on it, such as motor performance, temperature, ambient pressure, and the like. Now, if you wanted to instrument any of this and actually send it up to the cloud for inferencing, or use machine learning to see if there's any floating material inside of it, it's kind of more complicated to graph that on top. But by taking this application and run it on an IoT Core, you can take advantage of those workloads. So we're going to switch over to the side here. So you can see that this is the same application. It's actually the same binary that was literally copied off the desktop of Windows CE and dropped on top of the CE layer that we're talking about here, and it runs directly. In fact, you can see that it actually even has the CE start menu. Okay, and that's the only applications that's running inside of it. Awesome. Okay, thank you very much. Oh. Sorry, not done yet. So, we do really want your input. We want to see what you're going to do with this. So please visit the migration website here. We also have an IoT show where Deepu Thomas actually goes into detail about how this works and how you can take advantage of it. So please go ahead and register for more information. Okay, so now let's switch gears and talk about robots. I love robots. I used to work on Microsoft Robotics Studio. I was a dev lead on that. Robots come in all shapes and sizes, from little tiny toys that you can buy in the supermarket to building-sized material movers, and kind of everything in between. They are an IoT device, and that's actually really critical. They have the same needs and wants as a IoT device. It wants to be secure, wants to be manageable, wants to be useful and usable. Like other IoT devices, they also need to observe the world. They need to sense it, they need to understand it. What's different about robots is they can actually reason about it, understand the environment, and physically manipulate it. That's actually pretty cool. Let's see. We also think that robots are the best example of an intelligent edge device, because they need to be able to do all of this on the device itself. They need to be able to take advantage of understanding the environment. They need to be able to see it and reason about it, all with limited or potentially undesirable internet connectivity. Many companies are looking to onboard robots into their existing infrastructure. And a lot of factories and warehouses are Windows shops. So they want to actually make the robots that they're bringing on board work with their existing infrastructure. There is an open source framework that many of these companies are looking at called the Robot Operating System. Now, it's a little bit of a misnomer. It's not an operating system like Linux or Windows, but it's a middleware. It's an open source framework. You can think of it kind of like .NET Core or OpenCV. It is a way of building applications and a runtime for running them. We've been working with the open source robotics community and Open Robotics to bring ROS to Windows. We announced this at ROS-Con, which is a conference around ROS, in October. And I was a little worried that it wouldn't be accepted by the community. But I was really excited when the number of people came up to us and just said, thank you. Thank you for supporting ROS on Windows. I had one person come up to me and said, did you really support ROS on Windows? And I was like, yeah. It's like, okay, and he went away and he came a couple hours later, and they said, I've ported this major piece of code and it's working. It was pretty exciting times. So, what is the Robot Operating System? It is a mature framework. It was actually introduced in 2007 by Willow Garage, who was acquired and then spun out as Open Robotics. It is a framework for building robot applications. A robot needs to be able to receive data from a number of different sensors, operate on that data, and then actuate. And these are all happening at the same time. The way ROS handles this is it actually uses what's called an actor model. So instead of an object-oriented programming language where you have an object that you make a method call, you actually send messages and they're asynchronous. So you have things operating on data at different rates. To orchestrate that, there is a component called ROS Core, which allows pieces of the robot application to discover each other. And you can build what are called nodes. These are behaviors or skills for your robot. And they each run in a separate process. And they communicate with each other over IP. Now this is kind of cool because individual nodes can run on different compute units. So you can actually create a composition that takes advantage of microcontrollers or multiple different CPUs. A node can publish or subscribe to topics. A topic is like a named message queue that allows you to send data or receive data. And we'll show how this is useful. Now, if you're familiar with the Microsoft Robot Studio, you'll notice that this shares a lot of the same behaviors as Robot Studio did. So it's they have the same similar history. Microsoft is also a member of the ROS Industrial Consortium, which is looking to take this open source framework and make it industrial friendly. And it's joined by hundreds of companies that both produce robots, consume robots, or produce middleware for robots. There are nodes, skills, behaviors, drivers for all sorts of different components for a wide range of activities such as manipulation, mobility, even spacecraft, which is a lot of fun. So yesterday we actually announced that Windows 10 IoT is now a supported platform for ROS. We call it generally available. From the ROS community, they call it a supported platform. We've seen excitement both from the academic and hobbyist communities as well as the industrial communities who are excited about using ROS on Windows. So what did we actually announce? If you look at ROS as a whole, the robot operating system, there is the ROS Core. And this constitutes the build system, the messaging system, and a core set of nodes to start up and orchestrate your robotics workloads. However, ROS is actually a large community of nodes representing thousands of discrete behaviors and skills and drivers and compositions. We've taken a swath through mobility and manipulation. If you, down in the, what do they call it, the showroom floor, we had actually several different robots running ROS on Windows. We saw one in the Microsoft AI group as well as in the IoT group doing different tasks. Today I'm going to actually show you some of the mobility features using a TurtleBot. And I'll show you a little bit more about the TurtleBot. We've ported the top 40 meta packages, and a meta package is made up of tons of smaller packages encompassing about 300 repositories. So it was a huge operation for us and the community. We've also lit up a couple of Microsoft-specific nodes, including an Azure IoT Hub connector, which allows you to take ROS messages and stream them to the cloud, as well as a Windows machine learning node, which allows you to subscribe to camera data, run an Onyx model on it, and receive output to do something interesting. We're also working on a Visual Studio Code extension. Their most popular, there is actually a ROS Visual Studio Code extension today that was built by Dr. AJ Short. And we reached out and we said, we would like to add support for Windows and a couple of other features. He asked us to take ownership of it because it wasn't something that he was able to continue working on. So we're working through the logistics of that. However, I'll show you a couple of things that for Visual Studio Code. So here we have a ROS workspace. Now a workspace is kind of like the ROS equivalent of a Visual Studio solution. It's created with a ROS tooling, and you pull in individual nodes that you actually want to build as part of your robotics composition. One of the things that we're demonstrating today is what is called a URDF preview. Now in robotics, the position of a camera relative to, say, the keyboard, if we were using a laptop as an example, is actually of critical importance. Just a slight deviation in the position can actually radically change the behavior of a robot. So in order to connect sensors to actuators, they use a description format called URDF and a macro format on top of it called Zacro. So let's see if this is going to render. Okay, so it worked, yay. It's a preview right now, just got it working. What you can see here is the URDF is actually being processed locally and rendered. And that's a fairly accurate representation of this robot. Okay? You can see, you might be able to see in the links that connect various components together, such as where the wheels are in relation to the sensor on the top, as well as interesting things like the weight distribution of the robot, where the center of gravity is, because that's all taken into account during the simulation. We'll come back to the Visual Studio Code extension in a second. Which ones? Okay. That font is really small. So other things that are really interesting about the Visual Studio Code extension is it allows you to actually manage your robotics composition. As I mentioned, a robot is built up of many different nodes that are all communicating together. This allows you to start up the composition, shut down the composition, as well as other behaviors. Okay. So I'm going to show you in a minute a demo in simulation that is about navigation. So how do you actually get a robot to move around an environment? So this composition that we're using leverages one sensor, actually two sensors, and an actuator. The first sensor is a LiDAR, which is a spinning laser. And what it does is as it spins, it computes a distance to the things around it. And it knows the angle of which point when a sensor reading is taken. The other sensor we're using is the inertial measuring unit, which actually knows how far away it has deviated from a position. Between those two pieces of information, we can actually fuse all of that together into a map. For this demo, we're actually using a mapping technology called Cardo, which is an open source framework that we've enabled on Windows. And then we're using a localizer called AMCL, which allows you to take sensor data and turn it into a position. So how does this work? So first, we have the LiDAR and the serial bridge, the microcontroller bridge, sending data to two different topics. These messages are subscribed to by both the mapping technology as well as the localizer. And that's fused together in order to create information about its environment, allow it to sense where it is in space and what the space looks like. The cartographer is responsible for taking the fusion of that data and publishing a map. And the localizer is actually responsible for saying, here's where I am. This is the pose I have in space, which is the orientation and position relative to some global environment. Now that's all well and good, but if I can't go from point A to point B, what use is a robot? Well, this is where move base comes in. Because the position fuser will actually say, this is where I am relative to the world. And the move base actually says, here's how I create a plan to go from point A to point B. Now, a robot's just going to sit there unless it has something to do, and this is where your robotics application comes in. It gets a mission. That mission can come from a cloud service, it can come from a human, it can come from a behavior that you've coded that just says, I'm bored, I want to do something. It creates a goal and says, go over here. That goal is attributed to move base, which generates command velocities, which closes the loop back onto the environment, or onto the robot itself. Okay, so now we're going to switch over to the second demo. So in Visual Studio Code, I can bring up the environment and launch a ROS launch file. This particular ROS launch file exists in the Build 2019 demo, and it's called sim.launch. Okay. While that launches, we're going to talk a little bit about what's happening here. So first, we're actually starting the composition. We're actually launching this launch file, which is kind of like an auto-execute.bat, if you remember those. That launches a whole bunch of executables and says, here's the parameters associated with those binaries. As it starts up, we also launch what's called Gazebo, which is a simulator. This simulator actually implements the robot, and it allows the code that is running behind it. It doesn't really have to care whether it's running on a robot or in simulation. It's just getting data from the environment, processing it, and doing something with it. This particular environment was built by Robotics for their TurtleBot line, and you can actually buy this from their website. We just picked one up and using it for the demo. And we're also using their demo code for this project. So Gazebo, as a simulator, has physics. If you hit a wall and the wall isn't fixed in space, it'll knock the wall over. you can actually knock your robot over if you're not careful in simulation. It's pretty neat. So on top of the simulator, we're actually going to take a look at a visualizer. Now the visualizer takes information from the environment and actually shows you what the robot is seeing. Okay, so in this case, we're going to go ahead and launch a previously stored visualizer. That's pretty cool. So what we're seeing here is a couple things. First, I'm going to actually turn off one of these maps. Okay, so this map was previously generated. I drove it around and it figured out where everything was. And it's called what's called an occupancy map. That's about 5 centimeters blocks. You either can go there or you can't. So that's saved off and used for navigation purposes. We can also do something like visualize the scan. So I'm going to go ahead and make this visible. Let's say 10 points. Okay, so these are LiDAR points, the green, which is simulated from the Gazebo simulator. This is all open source code that's been built by the ROS community over time. So we're just showing it running on Windows. As the simulator is generating these rays, we're actually receiving that as input. And the localizer is doing what's called a cost map, which says, so what a cost map is how costly is it for the robot to move into a certain spot. And this takes into account certain things, like I want to be this far away from an obstacle. I want to optimize for being away from things that could cause me trouble. And in this case, the blue is a place where I can go freely, and all of the red is where it gets more costly. It'll try to avoid getting near red until it actually gets to that cyan thing where it's a no-go. So we're going to create a nav goal, which basically says, I want to go here and face this direction. Now, as it's moving around, we're going to go ahead and take a look at what the cost plan, or the plan is. So we can see the map, that's the trajectory that has been generated. Again, this is all open source code that now works on Windows to be able to build your robotics solutions. So to learn more about ROS on Windows, please go to aka.ms/ROS. This will take you to a landing page where you can actually go off to the ROS wiki, which will show you how to install ROS on Windows and start working with it today. Our community is the ROS community. So when you go through the ROS community, it'll point you, or go through our community link on the landing page, it'll take you to the ROS community. We're monitoring the ROS community as well as Reddit for any support issues. And with that, I'm going to hand it back to you. Thanks.
Awesome, Lou. Thank you very much for that. I told you he was brilliant, and he did not disappoint. So thank you, Lou. Thank you very much, everyone, for having made it this far in build. And we're almost to the end. And so just a big shout out from all of us at Microsoft for you coming here to our hometown and attending. I just put together a little quick thing for you to snap of kind of summarizing the various things that we talked about here. After the talk is over, there'll also be folks from the Windows IoT engineering team up near the stage over here, and you're welcome to come and approach with questions that you may have about technologies that we discussed today, or things we haven't discussed today, or your favorite pet peeve that you want to remind us about. Doug, you're welcome to bring those up too. And we'll be right over here for that. So thank you very much on that. And then, of course, we value your feedback. So if you liked the session, give us feedback. If you didn't, you probably should too, and just tell us, how to make it better for next year. Because we'll be here next year talking about Windows IoT then as well. So thank you very much.